Welcome everyone to our webinar on best practices for optimizing compressed air purification. My name is Luana Cruz and I will be the moderator for today's session. So, before we begin, please note you're welcome to add your questions in the chat at any point. We're going to address them during the Q&A session. So, let's get started. So, before I hand it over to Wolfgang, I would like to go over who we are and what is our purpose. At Donaldson, our sustainability strategy, Filtration for a Thriving Future, focuses on creating a positive impact through our products, practice, and people. It's how we support a cleaner world today while building a better future for the planet and future generations. So, Donaldson is a global leader in filtration. The numbers and visuals here on these slides give you a quick snapshot of who we are and what we do. So before we continue, I just wanted to give you a few points. We work across many industries, offering filtration solutions for a wide range of applications. This broad experience helps us create innovative solutions that meet different customer needs. By sharing knowledge and technologies across our global teams, we solve some of the most toughest filtration challenges out there. So to sum up, filtration is what we do every day in everything we make. We operate in over 140 locations worldwide. Our extensive network ensures that while we have a strong global presence, we maintain a local touch, offering support, service, and expertise whatever it's needed. So, with that in mind, let's dive into today's topic, compressed air purification. I'm pleased to introduce you to today's presenter, Wolfgang Bongatz, a Global Product Manager for Industrial Gases at Donaldson. Wolfgang, thank you for being with us today, and the floor is all yours.
Thank you, Luana. Before we are starting to talk about the purification and optimizing it for the compressed air systems, we need to look on the general concepts of compressed air. So, compressed air originates from the compression of atmospheric air, and the atmospheric air is consisting of nitrogen with 78%, oxygen with 21%, and some other gases with 1%. Imagine you have these atmospheric air at atmospheric pressure, and the atmospheric pressure is 1 bar. And then now you start to put it in a closed volume and starts to compress the air. For instance, to an overpressure of 7 bar. That means by adding the atmospheric pressure of 1 bar, you have a total absolute pressure in that smaller compressed volume of 8 bar. And this small volume contains a lot of energy, what you can use for different purposes, for instance, in the industry. And that's the reason also why after electrical energy, compressed air is the second most used energy source in the industry because it has a lot of advantages. First, it's a compressible fluid. It's a carrier of heat energy and especially on mechanical energy. It is lightweight compared, for instance, to hydraulic systems. And it enables high-speed moving processes. While it is simple and safe, that means even if there is a risk on having a compressed gas, there are standards and design regulations and rules available which make it applicable in a very simple and safe way. And last but not least, it's a very easy storage of energy. With all the advantages, we see compressed air in many, many applications. It starts with moving and actuating processes. It can be used for drying, cooling, and purging purposes. And if you are mixing it with other fluids, it can be used, for instance, for painting applications or for aeration processes. Also, it can be used to transport, for instance, bulk materials in conveying processes. In food and beverage processes, we are finding a lot of applications in blowing, filling, and packaging processes like PET bottling and filling with beverages. It can be used for industrial and medical breathing air applications, of course, with some higher requirements for purification. It is used in controlling, measuring, and testing processes, such as leakage testing, for instance, or pressure testing. And last but not least, in chemical processes where the air is used in a certain process, or for gas generation. That means if we are talking about air separating into nitrogen and oxygen. But with the compressed air system, we have to take care of pollution. And I would like to talk about some specific pollutions, a little bit more specific in that next section here. So first we are having the atmospheric pollutions, which can come from different processes, from the industry, from traffic, but even also from natural sources, like particles coming from pollen or just, let's say, dust in the air and humidity. So all these pollutions are coming into a compressed air system while they are sucked in by a compressor. And as a first part, I would like to have a quick look on the solid particle layers and aerosols pollution. So aerosol, this is a suspension of solid particles or liquid droplets in a gas. So if we are talking about particles, they can be either solid or liquid. And in that chart, what you see here on that slide, you see different particle sizes and examples for different particles or aerosols, starting even at gas molecule size of 0.001 microns and ending up in coarse dust, or even here like beach sand in a couple of millimeters in particle size. I highlighted on this chart here two specific aerosols which are frequently being in compressed air system, especially when we are talking about oil lubricated compressors. We are finding a lot of oil aerosols in the compressed air, and due to the compression process and the cooling downstream the compressor, we find a lot of water aerosols. You see that sizes of these aerosols are different. So water aerosols are usually much larger than the droplets in oil aerosols. So it's more challenging to remove oil aerosols rather than water aerosols. But there are solutions available in specific filtration systems like coalescing filters, which can help also to remove these oil aerosols. Maybe an interesting information here is also atmospheric air can contain, let's say, 150 million particles per cubic meter. Usually 80% of these are smaller than 2 microns and are not retained by a compressor suction filter. That means from the 150 million, 120 million are still coming into a compressed air system and can contaminate that. Gaseous components are also important, not only because they are poison, like carbon monoxide. It's also because a lot of them are creating corrosive environments inside the compressed air system when coming in contact with liquid water and forming a condensate, such like carbon dioxide and nitrogen oxides, sulfur oxide, ammonia, and ozone. This can be very critical components, and you need to take care of selecting the right material in order to avoid corrosion in your processes, especially in that areas where the compressed air system is not purified and not dried. Talking about drying, we are talking about the contamination by humidity, like water vapor or liquid water. And in the terms of reaching a specific dryness level, we are talking about dew point. So dew point, you know that compressed air or air at a specific temperature can only take a specific amount of water. And it's depending on the temperature, it's increasing in an exponential way. Okay, so that means there is a saturation curve. That means if we are going to cool down air volume to a specific temperature, condensation starts. And the point at which the condensation starts is called dew point. And this dew point, it's also reached when the relative humidity has reached 100%. And that temperature related to the starting of the condensation is called the dew point temperature. In compressed air systems, we have to differentiate between the atmospheric dew point and the pressure dew point. So in compressed air systems, we are talking about pressure dew point. And this is the dew point at a certain pressure. And this is also something where you have to take care of, because always when a dew point is mentioned, the pressure should always be mentioned with it. Oil. Oil in liquid, aerosols, and vapor state comes into the compressed air system in oil lubricated compressor systems, of course. And here on the right, you see the chart of a compressor with, and you see two loops here. One is the part for where the compressed air is going through, and the second one, the yellow one, that is the oil loop. And it starts here in the compressor already at the suction filter at this point here. And when it's sucked into the compressor stage, then it is mixed with oil, which is injected into the compressor. And at the outlet of the compressor stage, we are finding a so-called air-oil separator, while the majority of the oil is retained again and is feeded back into the oil loop. In the oil loop itself, there is also an oil filter comparable to what you know from your car, and which is removing particles in the oil loop. But more important here for the compressed air quality is also the retention efficiency of these air oil separators. So that means at the outlet of the compressor, there is always a certain amount of oil aerosols. And the better the air oil separator, the better is also the purity, or the higher is also the purity of the compressed air. The amount of oil which is going into the compressed air system is depending on, for instance, the type of compressor. Piston compressors usually are releasing more oil than screw compressor, or even oil-free compressors do not have any oil in it, of course. Efficiency of the air oil separator is very important, as I already mentioned, but also the compressor age and condition, and if it is maintained regularly, that's also very important. And last but not least, the type of oil. So mineral or synthetic oil. Usually synthetic oils are releasing less oil vapor than mineral oils. Looking at the compressed air system pollution, again, this is also depending on the pressure in the system. So everything which is sucked in from the ambience, like water, humidity, particles, gaseous components, and microorganisms. And in the compressor, there is oil also added into the system. We can say that in the compressed air system where the pressure is higher, the concentration of the contaminants is also much, much higher, because you are compressing the volume, but the amount of contaminants are staying the same. So in a smaller volume, you have more let's say, gram per cubic meter than in an air volume at atmospheric pressure. And that makes it also challenging to remove these contaminants. And what is happening if you are not taking care of the purification system and not trying to optimize it, the consequences can be that you find really particle contamination here. This is, for instance, a filter downstream, a large heat regenerated adsorption dryer, and the dust, what you can see here on the filter elements, that is dust from the desiccant, because the desiccant was floated with water from upstream the adsorption dryer, and that damaged completely the material, and last but not least, it ended up in the dust filter downstream the adsorption dryer. Corrosion, here, that is the filter housing, and you see there was not the right material selection when using this filter housing. Maybe it would be better to use in that application here a kind of stainless steel material in order to avoid these corrosion effects. Water contamination plays also a very important role. Sometimes it's unbelievable how much water is generated from a compressor system, depending also from the ambient temperature and the cooling system. It might be that there are hundreds of liters per hour coming into a system, and if this is not maintained and managed perfectly, then you find really issues then with floating your compressed air system with water. And last but not least, chemical impacts. These are some filter elements in the filter housing, and you see there's a drainage layer around the filter elements, and that has been completely damaged by a chemical impact, so that the filter as such is more or less useless in the end. And if you are talking about purification, then there is one important standard existing in the compressed air world, and this is the ISO 8573-1, which is defining the compressed air purity classes. This table here gives the overview about the purity classes, and on the left you see the purity class numbers. That means the lower the number, the higher the purity. And this standard is focusing on three main contaminants. It focuses on solid particles, on water, and on oil. Particles, they are clustered in three different particle size ranges, from 0.1 to 0.5, then larger 0.5 up to 1 micron, and larger than 1 micron up to 5 micron. And you see, if you want to achieve the purity class 1, then the numbers here are giving the remaining particles in the already purified compressed air, so downstream a filter. That means for these very small particles, even class 1, which is a very high or the highest defined class, it allows to have 20,000 particles in that range here. Yeah, for dew point, for water, it's defined mainly by dew point, because if we are talking about purity, then we are focusing here on the classes 5 to 1 or 1 to 5, where in the industry very frequently you will find the definition of purity class 2, which is related to minus 40 degrees Celsius pressure dew point or minus 40 degrees Fahrenheit. Okay, and for oil, this is defined in total oil. That means this is the combination of liquid oil, so aerosols, and oil vapor. And this is really important because sometimes the oil vapor content might be higher than the liquid oil content. Yeah, and so the definition of these purity classes is always in the same sequence. That means reading from left to right, the first number always stays for the solid particle, the second one for water, and the third for oil. it's important why I'm explaining this, because in the next slides, we need these definitions in order to define at specific points on our compressed air system, the purity levels. Okay, now we are talking about industrial gases purification solutions. And it starts already with the compressor. I explained that briefly. There are these three important filters inside of a compressor. So first, the inlet air filter, which has an effect on the two other filters, on the oil filter and on the air oil separator. So the more particles and contamination you can remove already by the inlet filter, the less will end up in the loop filter or in the air oil separator. So also for the oil filter, that has also a big impact if you are removing also some contaminants like particles very efficiently in that stage. That helps to have a perfect retention efficiency and lifetime of the air oil separator. And the better the air oil separator works, the better the purity or the higher the purity in your compressed air system is. So it's very important to look also on these filter and especially on the air oil separator. Donaldson is providing really an outstanding coalescing media technology, which make this type of filter very, very efficient. Looking at downstream of the compressor, so in the compressed air system, you see that for each of these contaminants you find here in that table and in the header, like for particles, there are specific filters designed to remove particulates very efficiently. Yeah, and in order to also to achieve the quality classes as defined in the ISO 8573. For removing oil or water aerosols, and here it's playing a role that we are having a very high efficiency, especially for these small oil aerosols in the system. We have these so-called coalescing filters, and also here specific media technology like the ultrapleed technology. And what's also important is that for these coalescing filters, that they are always equipped with a appropriate condensate management systems, so condensate drains. And ideally, these are electronic ones with sensor inside, which is only releasing the liquid, so the condensate from the compressed air system, but avoiding that any compressed air is lost during the draining process. Oil vapors or even type of hydrocarbons are usually retained in activated carbon filters or absorbers. And the selection, if you are going with a filter or an absorber, that's more a question of the lifetime and also on the operating conditions. So the higher the temperature, also the higher the oil vapor content. And then it might be that a simple filter, a small filter element, filter housing, gives only a couple of thousand operating hours before it is saturated, while an absorber, which is really filled with a lot of material, activated carbon material, has a much, much higher lifetime. Liquid water. It's very easy. You can just remove it by adding another cooling system. So like a water cooler, okay? An after cooler with water as cooling media. But when doing that, you have to take care also to have a separator installed downstream of the cooling system in order to remove the bulk water which is coming from the condensed water vapor in this after cooling system. And if the condensate is containing not only water but also residual oil, then you have to apply also oil water separators in order to separate your condensate. Talking about water vapor, we are talking about these drying systems. And I have separate slides for the different types of dryers, so I'll leave that out here, explaining that in detail. We look at that a little bit later in another slide. And last but not least here, other gaseous contaminants or special gas applications. We have also solutions for this. So specific breathing air systems, which are removing the contaminants defined in the regulations for breathing air, are retained here. But Donaldson is not only active in the compressed air world, but also we are strong in gas applications such as hydrogen and biogas applications. Now, I think this is the important slide here for defining how from source to application, a purification system can be set up to be very efficient. So it starts with the generation, with the filters inside of the compressor. As a next stage, we are finding usually a cooling and a separating area with an additional aftercooler. And of course, downstream the aftercooler, there should be a cyclone separator in order to remove the bulk water from the cooling system. Also, usually we are finding air receiver vessels in a compressed air system. Also here, it's important to have a condensate drain installed, especially if it is installed upstream the dryer parts. And then our recommendation is that we are adding already a pre-filter before we are going into the, let's say, more sophisticated purification area and purification processes like drying. So in the inlet of a dryer, it would be sufficient if the purity classes for particles are already in the purity class 5, and for oil in purity class 4. That means a coarse filter would be sufficient to achieve that. And then the question is what you want to achieve in the next purification stage. So if for a specific application it's okay to have just the purity class 4 for water, then you can go with refrigeration dryers. Okay. But if you are going that way, it's also important to know that even downstream a refrigeration dryer, it can be that there are still some remaining small oil aerosols. Therefore, we are always recommending to have another coalescing filter installed downstream a refrigerant dryer. If you want to have a higher dryness level, let's say dew points of minus 40 degrees Celsius, then you can go with adsorption dryers. Usually for Donaldson, we have in most of our dryers, especially in the heatless dryers, always pre and after filters already installed in the package. For larger systems, such as heated dryer systems, the filters are installed separately from the dryer in the compressed air system. And in the next stage, you also need to take a decision if you are going either with activated carbon filter or with activated carbon adsorbers. You see that the oil purity class moves from 2 to 1. So here, then after downstream activated carbon, we can really confirm that is purity class 1 is achievable here, depending on the operating condition and the sizing, of course. But you see, depending on what way you are going, it might be downstream an activated carbon adsorber. There is still some remaining particles released from the activated carbon material in there. And therefore, we are recommending also to have always on the last part of the system another particle filter installed, and then you can achieve even again particle class 1 for your purification system. Okay, looking on the drying technologies, starting with the refrigeration dryers, how is it working? So the general principle is based on condensation technology. So we have two heat exchangers in here, while the wet air is coming in the first heat exchanger, then passes into the second one. And here we have a refrigeration circuit installed to it. And this is bringing the temperature down to the dew point of about 3 to 5 degrees Celsius. Usually 3 degrees Celsius is the characteristical dew point in that systems here. And it's above 0 degrees Celsius. Otherwise, there is a big risk that that the liquid water starts to freeze in the refrigerant dryer. Okay. Downstream, these cooler, we have, of course, again, a separator, which is removing the liquid condensate from the system. And then here at this part, in the lower part, after the separator, the air is cooled down to a pressure dew point of 3 degrees Celsius and also to a temperature of 3 degrees Celsius. And therefore, it's important that we have this air-air heat exchanger, and the wet inlet air is heating up the air from out of the refrigeration circuit heat exchanger again. And here at the outlet, you have a dew point of 3 degrees Celsius, and your relative humidity is in the range of, let's say, 10%. So the air is really, really dry when it comes here to the outlet. So what are the advantages from this system? There is no compressed air loss needed for the drying process. The energy consumption is really fair. It's not that high. Of course, we have a compressor in there in the refrigeration circuit and a condenser with a fan, but it's not that super high. Okay, and the initial costs are also fair compared to other systems. Disadvantages. Here we are using, of course, refrigerant in the refrigerant circuit, which is not very environmental friendly. And the pressure dew point, the minimum pressure dew point, what can be achieved is 3 degrees Celsius. This is not sufficient for all the applications. Therefore, in order to get a lower or a higher dryness level or lower dew points, we need to go with adsorption technology, so-called adsorption dryers. And the first one, mainly used for smaller and medium-sized applications, are heatless adsorption dryers. So they are working in the principle for adsorbing water vapor or water molecules on a hygroscopic desiccant. And this is filled in two pressure vessels, while one pressure vessel is drying the compressed air. In the other vessel, the saturated desiccant, because that can also pick up only a certain amount of humidity and water, needs to be regenerated. And at heatless dryer systems, we are using a portion of the already dried air, leading it through the desiccant, and this is then picking up the water from the desiccant. The downside of this process is it uses a portion of the compressed air. So in the range of 15 to 25%, it's depending on the achievable dew point. So minus 40 degrees is the standard, but it can also achieve in certain sizing and operating conditions minus 70 degrees Celsius pressure dew point. So really class 1. So the advantages of these systems is it's generating really a stable dew point at all ambient conditions. Even these systems are working in tropical environment very well. The initial costs are also relatively low compared to more complex system, but the disadvantage here is the loss of purge air, which is compressed air from the system. So, and in order to avoid the loss of compressed air, and also very attractive here for more larger applications or larger size compressed air systems, are the heat regenerated adsorption dryers. Also, there are multiple systems existing. The most energy efficient ones are the ones with no purge air loss. these are also models that Donaldson is providing in our Ultra Dryer Plus product range here. So here the regeneration of the desiccant is not done with a portion of dry air, but with ambient air. So ambient air is sucked in by a blower, heated up by a heater, and then due to heat, the water is evaporating from the desiccant, and then it's ready also for the next drying cycle, and no compressed air is lost here. There is one exception on the model HRE. This is a model where at the end of the cooling process, a small portion of cooling air is added in order to dry up the desiccant a little bit more. This is especially if you are using this heat regenerated dryer in tropical environment or in subtropical environment. So also here the advantages are a stable dew point, no purge air loss in the system HRS and HRSL. Of course, as you can see from the chart here, it's a more complex system, so the initial costs are higher than on the other two dryer types. And of course, there are some electrical energy costs coming with the blower and the heater. But in the end, it's more efficient long-term in total cost of ownership because it's not using any compressed air for regeneration of the desiccant. Yeah, maintenance for reliable performance. That's also an important part. And here, Donaldson is also strong because we are providing service and support for you. And these compressed air and gas services include breakdown interventions, inspections, system measurements and audits, parts and service, of course, preventative maintenance, project commissioning and retrofits. Also for existing units, we are able to upgrade these systems in the field. Of course, new installation of new equipment and piping design and installation. That's where we are strong. It's not only for the compressed air systems, it's also for other systems where Donaldson products are used in the industry, like dust collectors, for instance, which might end up in the same facility like the compressed air system. Okay, so why choosing Donaldson? So we have a really outstanding technical filtration expertise. That's the core of our technology. We are providing superior customer service, operational excellence, and we have an extensive global footprint. So we are everywhere, and last but not least, we are a value-driven team. So thank you for attending. Thank you for listening. And now we are opening up here for question and answers.
Thank you, Wolfgang, for the presentation. Now we are going to start the Q&A session. So our panelists for this session are Wolfgang Mongarts and Simon Bevres. Simon is the sales leader for North EMEA and Export. So we have received a lot of questions in the chat. So I'm going to start with the first question. What services packages does Donaldson offer for its range of dryers?
I'll take this one, Wolfgang. It's quite unbelievable how many part numbers we have with our business servicing the installed base that we have globally. So we break it down into minor service kits, major service kits, and we try and do the preventative maintenance. It's all about preventative maintenance to ensure that our customers don't have any quality issues with the product within its serviceable lifespan. And that can range from inlet filtration to desiccant media to solenoid valve diaphragms, silencers. The list is quite endless. It's really important for Donaldson to ensure that this equipment is doing exactly what it needs to do. So any dryers out there, even competitor units that need maintenance and service packages, either for 1 or 5 or 10 years, then please get in contact and we'll happily find a solution for you.
Thank you, Simon. Coming up to the next question, when should you choose a desiccant dryer over a refrigerant dryer?
Yeah, I can take the answer here. Desiccant dryers are usually required for pressure dew points below 0 degrees Celsius. So for more demanding applications, such as food and beverage applications, for instance, where also low dew points are required in order to avoid bacteria growth in the system. But there are many other applications which require the low pressure dew points, in critical applications. So everywhere where you need to, for instance, also to avoid freezing of the compressed air, where there's a risk that the temperature falls below 0 degrees Celsius, it's also recommended to use desiccant dryers.
Thank you, Wolfgang. Going up to the next question. This one here is divided in two parts. First part is, can compressed air leaks reduce system efficiency? And then second part, how can Donaldson help identify and fix these leaks?
Okay, Wolfgang, I'll take this one. Compressed air leaks, massive, massive subject. Every single system will have compressed air leaks. What is a compressed air leak? It's a wastage of energy. Compressed air is very expensive to generate. And if you have leakages, it increases demand on the entire system and increases the kilowatt hours that you'll be required to generate that leakage. So having an annual or regular leak survey is something that we offer within Donaldson. Using our ultrasonic leak detection equipment, we can scan your production, identify the severity of the leak to give it a priority, and then build a plan for either your maintenance teams or assisted by ourselves to help in repairing these leaks, to ensuring that we're giving you the most optimum efficiency, reduction of kilowattage, and saving operation cost. So yes, we have that capability within our massive service fleet within Europe.
Thank you, Simon. Coming up to the next question. To reduce pressure drop, should I maintain larger filter housings even if their capacity exceeds the system's maximum flow?
Yeah, I can take the question. That's a quite common solution in order to reduce a pressure drop or the differential pressure in the system, and it also supports more energy efficient operation. A little bit like leakages in the system. This pressure drop is also requiring then the compressor to run at a higher pressure than usually needed for the application. So that means the lower the differential pressure, the lower the energy consumption from the compressor. And therefore, it's also a recommendation from our side to do so. So oversizing a system, maybe also adapting the like filter housings, for instance, to the size of the pipeline system. That could also help in some instances. That has to be balanced a little bit to use the correct flow rate and the size of the pipeline system, of course. But in the end, it's always a good idea to oversize the filters in a compressed air system.
Thank you, Wolfgang. Moving up to the next one. How can we achieve breathing air quality?
Yeah, I can take this question as well.
Yeah, you take this.
Breathing air quality. So we have dedicated system solutions. We saw that in the presentation, in the overview of our products. So we have specific solutions for generating breathable air or breathing air according to the regulations and standards. So that means this is usually a combination then of an adsorption dryer, which is removing not only the moisture, but also, for instance, the carbon dioxide in the system. More critical is removing, of course, carbon monoxide as a poison gas component. So there's specific catalysts used in our adsorbent and catalytic system in these breathing air units to remove this. And of course, oil vapors and contaminants like nitrogen oxides or sulfur dioxide, which is a contaminant where there are strict regulations, especially for medical breathing air applications. That's all something we have under control. And we have also validation certificates, which give a clear statement of that our products are achieving the required regulation. For instance, for medical applications, it's the European Pharmacopoeia.
Perfect. Thank you, Wolfgang. Moving up to the next one. With increasing restrictions on certain refrigerants due to their GWP, am I safe from these concerns if I use an absorption dryer?
Yeah, I'll take this one, Wolfgang. Yes, in brief terms, yes, you are, because we don't use any toxins or refrigerant gases within the desk and dryer systems. It is a constant changing field in what gas is appropriate or can be used within EMEA and globally, and getting more and more stringent year after year. So it's a little bit uncertain where to go with the refrigerant dryers, but upgrading the air quality to an energy efficient absorption dryer. Obviously, it costs more energy to run the absorption dryer than a refrigerant dryer, but the quality you achieve is far better. But it will also really ensure that we have no risk regarding GWP moving forward, and the equipment is potentially going to be available for a lot longer period.
Great. Thank you, Simon. Moving up to the next one. What type of filter media is recommended for applications requiring minus 70 degrees pressure dew point?
Okay, this question is about filter media. So we are talking here in these in the desiccant dryers about desiccants and adsorbents. And what we are using here is usually a kind of hygroscopic material. Which can achieve dew points also down to minus 70 degrees Celsius. For instance, with a molecular sieve desiccant, that's applicable to generate minus 70 degrees Celsius pressure dew points in different type of dryers. So it's not only applicable in one specific dryer type, like the heatless adsorption dryers. Also, we have solutions in heat regenerated adsorption dryers to generate, for instance, with a closed loop regeneration system to generate the minus 70 degrees pressure dew point.
Thank you, Wolfgang. Moving up to the next one. I'm not sure what ISO class on air quality our system is achieving. Can Donaldson help assess our current air quality and recommend improvements?
I'll take that one, Wolfgang. Yes, we can. We have quite a large business of air validation testing, where Donaldson will come to site, install the equipment onto your gas lines, onto your compressed air lines, and other gases, to measure the pressure dew point, hydrocarbon content, particulate size. And from that, we can do a survey on how to meet the efficiency level that you require at the optimum cost. So yeah, please get in contact and we'll be happy to come and do the site survey with you and your quality control.
Thank you, Simon. Next one. Why are ambient conditions so important in the dryer sizing process?
Okay, so I take this question, Simon. Okay, we have to differentiate what kind of dryer type. It's important for refrigeration air dryers, and it's important for dryers, heat regenerated dryers working with regeneration air sucked in by a blower from the ambient. So in these both dryer types, it is important to have that under control. Why? Because that has a direct impact on the achieved dew point and performance of the dryer. If we are talking about the heat regenerated dryers, there is really a restriction in a specific temperature and humidity range. In order to achieve the required dew point at any time. So sometimes we are recommending then to use, again, these closed loop regeneration systems, which is also independently cooling with ambient air. Or we are recommending to use the models consuming a very small portion of already dried air for only for during the cooling process.
Thank you, Wolfgang. I see here that we are still receiving a lot of questions. However, our time is almost running out. So we are going to be following up in all of those questions. We are going to be sending you all an email with our replies with a follow-up to all of that. For now, I would like to thank you, Simon and Wolfgang, for your participation, for your answers. I would like to thank you all for attending this webinar and hoping to hear from you soon.
Okay, thank you, everybody.
Thank you.